That's recording, right?
I hope so.
All right. Nobody breathe. No. So this is the situation. Instead of having a string attached, we have a second support, a fulcrum, and we're also adding an extra weight, an extra mass. This object, the board, is in equilibrium, and using this fact and this data, we can solve again for the magnitude of normal force on the left and normal force on the right. So I'm going to give you a minute to copy the picture and the numbers so I could switch to the camera. Shoot. My alarm's gonna go in a minute.
Oh no.
All right, doesn't matter. I'm gonna shut it down. I can edit the video on my Mac. All right, so can I switch to the camera?
No, not yet. I'm sorry, there's a lot on.
Okay. By the way, for your better visibility, you could have moved over there.
I know.
If you have an opportunity to improve your life, you should use that opportunity.
But not everything can be. Those are some very good words of wisdom.
That's just common sense, I think. Although I don't know the difference between wisdom and common sense. No one knows.
Wisdom implies knowledge.
Man.
Common sense is intuition.
I wouldn't say so. So I'm switching to camera, right?
I thought I could put a hole in the wall.
That's my technique with
Just whip it.
I dart the
So-
ball at the compass.
I don't
Got a
know.
chance to go
Philosophy
in.
of intelligence.
So ladies and gentlemen, first we draw a picture, of course. That's the picture. That we have to convert it into a diagram.
So you got the forces.
And how many forces are acting on the board? What do you think?
1, 2, 3, 4,
Way too many.
4.
Normal force number one, normal force number two. There is definitely force of gravity,
And then what?
and there has to be a force because they touch each other. Every force has a source. If there is no source, there is no force. For the force of gravity, the source is the earth. For other forces, we have objects which touch. This force is a little bit tricky. This is the force acting on the board from this weight. How do we find the magnitude of this force? That's the normal force number one and the normal force number two. The force of gravity acting on this board is equal to the same number we got before, 0.5 times about 10, 5 newtons. What about this one? Do we know anything about this object?
Yes.
We know the mass,
0.3 kilograms.
0.3 kilograms. But if I want to calculate the force acting on this object, mg, that will be 3 newtons. That will not be the force acting on the board. So we have to apply some law which would relate these forces. Any suggestions? So, I'm gonna enlarge this picture. This is a piece of a board. That's this weight. This is 3 newtons. The force of gravity acting on this weight from the earth. But there is also a force acting on this weight from the board. And these two forces must cancel each other because of the Newton's second law. So this force also should be equal to 3 newtons. But this is not the force acting on the board. This is the force acting from the board. The force acting on the board, this one, points in a different direction. But what do we know about these two forces?
They equal 0.
They can't be equal 0, they already equal to 3.
Well, they cancel out to equal 0.
Now they can't cancel out because they apply to different objects. This is acting on the weight from the board. This is acting on the board from the weight. So, what do we know about these forces?
Okay.
Two forces acting between two objects.
Zero.
3, not 0. Hit the wall. The wall hits you. Why? What did you say?
But it exerts the same force back.
Yes, and that statement has a name, the third Newton's law. So according to the third Newton's law, the force acting from board on weight has the same magnitude but opposite direction as the force acting from weight on board. So this red arrow also should be equal to 3 newtons. That's a connection. The force of gravity is acting on the weight, but that force is compensated by the force acting from the board on the weight, but the weight acts back on the board, and they all have the same magnitude. 3 newtons. And what I want now is just forget about everything I said. Just draw a board and forces, that's it. Because all other elements, not important anymore. There is a board. You just don't have to be bored. Force of gravity, 5 newtons. This force has no name, applied force, 3 newtons. 2 normal forces. Normal number 1, normal number 2. Now, distances. The whole length is 50 centimeters, 0.5 of a meter. So that's gonna be, again, a half of that, 0.25 of a meter. Now, if you look at the picture, this distance is equal to 5 centimeters. Oops, sorry, the board is longer. 5 centimeters here, 5 centimeters here, 5 centimeters here. That's the picture. 5 centimeters, 5 centimeters, 5 centimeters. So in meters, 0.05, 0.05, 0.05. And now we have to choose what?
Origin.
Origin. Where can we choose the origin?
Wherever we want.
Wherever we want. Where do you want to choose the origin? What does the rule of thumb say?
Choose the axis. To be of the unknown force.
Yes, at the location of the unknown force. So we can choose it here or there, your choice,
Left side.
left side. So we choose the origin here. Now, 1, 2, 3, 4, 4 forces. For each force, we can write the magnitude of a torque first, the magnitude. So, for the normal force number 1, the magnitude will be equal to what number? 0, because we don't know the force. However, there is no distance from this axis to this force. 0. The next magnitude, let's go to gravity. Well, I'm going to call it 5 newtons. So, according to the equation, that should be equal to force times the lever arm. The lever arm, shortest distance from the axis to the line of action, should be equal to what number should I write for this? 0.2, yes, 25 centimeters minus 5 centimeters, 20 centimeters, or 0.2. So that gives me 1 Newton times a meter, which exactly same number as we had before, because nothing changed for this part of the calculation. Now we have to move to the 3 Newton force and calculate torque due to that force relative to this origin. So, every time I use the same expression for the magnitude of a torque, force times lever arm. So, for the new force, I have to use the new values or new expressions. So, what number or letter should you use for this force? For the force? 3, of course, that's 3. That's not a tricky question. Times, but now I need this distance from the same origin, the same axis of rotation, to the new line of action. That's line of action. So what this distance should be equal to?
25.
Exactly. It's 0.25 minus 0.5 but and plus again. So, any questions on this part? 0.25, what is it? 3 over 4, 3/4, 0.75 a Newton times a meter. Are we done with torques? Not yet. There's one more force, and for that force, we need to write torque. Do we know this force? Do we know the value of it? No. So if we don't know, we keep the variable which represents that force. Times, do we know this distance? Yes. That distance should be equal to the distance between these 2 points. So that was 50 centimeters minus 5 and minus 5, which gives 40 centimeters. Do we see it? From here to here. 50 centimeters minus 5 on the left, minus 5 on the right, so it's 50 minus 10, 40 centimeters.
Do you mean
Which, yeah, I'm just waiting.
So that, because you see my face.
Yes, I can see your face.
Wouldn't that be 0.20 then? If you have the 0.05 on that side? Actually,
This is what we,
that one.
I don't see there. You can, so if you could come here, please. This is 50 centimeters.
Yes, and if we take the 0.05
And we take, that's correct, but this is what we need to measure from here, from the same axis to this.
But I'm saying from just because you have it written down, from this is the halfway point.
Oh, and why would I need the halfway point?
Because you
Why
have it
do I,
written down.
no, why do I care? This is 1 point, this is 2nd point, I need the distance between these 2 points.
I know that.
So I take the whole thing and I cut 5 centimeters on the left, and I cut 5 centimeters on the right, and what's left?
So then
That's exactly what I said.
that should be 0.20.
Wait,
Is that,
I
you
have
guys
a
get what I'm
question.
saying?
Yeah, no, I understand what she's saying.
You don't need the number, but because you have it written down.
Okay, wait, ready? This is confusing, you're right. So, if,
It's just the branch for the 0.25.
so you wrote this first, we said that halfway was this, 0.025, and that is half of 0.05.
That is correct.
Yeah,
But when you
But
take them
when
out.
I've never used it because,
but then you added these.
no, I didn't add any. See?
Remember you added these after and you were like, oh, it's supposed to be longer after the forces. So by adding 0.05 and 0.05,
Sorry.
Yeah.
See, that
yeah.
That's what I was saying. When you ended the curve, it was 0.20. When you extended the curve, then it made sense.
That's what you should have said. Mr. Reed, please extend the curve. That's not a curve, that's a bracket. That's a bracket. And now, it absolutely correctly represents the distance from the right end of a board to the middle point of the board. That is correct. When I extended it, I forgot to extend this line, this bracket, this curve.
So it looked like it went from fourth to fourth
Yeah.
instead of fourth to the end of the board.
So, that's what science is about, and that's what scientists do. First, they confuse themselves, and then they fix it. That's what science is about.
You are completely correct. My whole life is confusing.
You're a scientist. So,
Yes.
we have magnitude number 1, magnitude number 2, magnitude number 3, magnitude number 4. Now we have to make a statement about the actual value. Some torques might be positive, some torques might be negative relative to this axis. So for example, this is the line of action for gravity number 1. If I slightly bend these ends, that will be the direction. How do we call that direction? Clockwise. That makes the actual value, where is it here, negative. Next one, positive or negative? Still negative, no difference, still same direction. Negative again. Next one, positive or negative? That's counterclockwise relative to this point, and that makes it positive. So 0, negative, negative, positive. And if we add them up, the result should be equal to what?
0.
What should be net torque equal to? Net torque. Net torque. The word is, what is the word? Equilibrium. And when the object is in equilibrium, net torque is always equal to what? 0. So, if we add this and everything else, the resultant has to be equal to 0. So, 0 plus -1, -1 plus negative 0.75 plus positive normal force number 2 times 0.4, and the whole thing should be equal to 0. That's our equation. Any questions about it? That's the most important part, because when this equation is written, what else can we write? Physics is finished, done. So, now we have to do some mathematics. So -1 and 0.75 plus 0.4 times normal force equals 0. So 0.4 times normal force equals 1.75. Normal force will be equal to 1.75 375 divided by 0.4. This is the time when we need to
4.375.
take a calculator. I trust you, but I follow the rule. Trust, but verify.
What's the word? I like it.
All right, so we have one more force left to calculate.
Oh my
Um,
goodness.
but it's much easier to do now because,
I thought we already did that one on zero.
no,
No?
no.
Oh no.
See, this force,
It's torque with zero. Got it. Forget it.
this force number one, minus 5 newtons, minus 3 newtons, plus 4.375 newtons, together should be equal to 0 because net force also has to be equal to 0.
Thank you.
I just needed the picture here, so see. This is how we can see this force. Again, relative to y-axis, we have two negative components. That also positive, like this one. And now what we can do is solve it. That's going to be equal to 5 plus 3 minus 4.375. That's 8 minus 4 minus 3.625. Please check my calculation. I was right.
Yes, you were.
Done. Now, one last note. For the lab in the future, and I will repeat it again. Sometimes we know the forces, and we need to calculate the distance where we should apply the force to keep an object in equilibrium. It doesn't change the strategy, not a thing. It's just in the final equation, we will have a different unknown, not a force, but some kind of a distance, and we will have to solve it for that distance. Any questions?
I just have one.
Yes.
At the very beginning, where did we get the 0.5 for the force of gravity? It was 0.5 times 10. Where was the 0.5 from?
We just use the mass. Well, the mass of the board is
Oh.
equal to 500 grams,
Oh, okay.
which is 0.5 of a kilograms. So this force has to be equal to mass of the board times G, which is almost 10. So 5 times 10, 0.5 times 10, 5. Well, let's hope it's recorded.
Don't you ran out of room or something?